In this lecture, we are going to look at the well-known word matching algorithm by Thomson. So what is the word matching problem? Word matching is the following question. We are given a word U and a regular expression R, and we ask whether the word U contains a subword in the language of R. Now, why is this problem relevant? This problem is relevant for information retrieval. Whenever you want to extract information from websites, from text documents, from whatever. So basically your word U is the text document that you want to extract information from, and the regular expression R expresses a pattern that you're looking for, some piece of information that you're interested in. And you wonder, does your text document contain this piece of information? So you want to extract it from the text document. Now, Thomson has already in 1968 developed a very nice and efficient algorithm for this problem, and this works as follows. The first step is that we transform the regular expression. We extend it in front, so before the R we put sigma star. So this is short for the following. So if sigma consists of letters A, B, C, then sigma star means that we have A plus B plus C in brackets to the power star. So it's an arbitrary word over sigma. So we have an arbitrary word over sigma followed by a word in the expression of R. Now you may wonder, why do we put an arbitrary word over sigma in front but not behind R? And the reason is point 3 of the algorithm. We will stop the algorithm as soon as we have found an occurrence of R. So we will not read the word to the end. So therefore, as soon as we've reached the final state, we will stop. Therefore, no sigma star is needed behind the R. But we need the sigma star in front because we want to express that R does not need to start at the beginning of U, but it could start somewhere in the middle of U. Okay, so the first step is we transform the regular expression into this, and then we transform the regular expression into a non-deterministic finite automaton. Now, this translation from the regular expression into the non-deterministic finite automaton does not suffer from state space explosion. The number of states that we obtain in our non-deterministic finite automaton is a linear function of the size of the regular expression. So we may get more states, but only by a constant factor. So there's no exponential explosion here. Now we have constructed our non-deterministic finite automaton for this language, and we are now going to check whether there is an accepting path in this automaton for the word U. And how we are going to do this? We are going to use an on-the-fly construction of a deterministic finite automaton. So we do not convert the non-deterministic finite automaton fully into a DFA, but we only create those parts of the deterministic finite automaton that are needed when reading the word U. So we start with the starting state of the deterministic finite automaton, and then we generate only those states of the deterministic finite automaton that we visit when reading U. As already discussed before, this on-the-fly construction avoids the state space explosion that we would get if we generate the entire DFA. And now we do this on-the-fly construction, and we stop as soon as we have reached a final state. So as soon as we've reached an accepting state, so we found a pattern that is in the language of R, then we stop the algorithm and we say that we have found the pattern at this and this position. So this algorithm is very efficient, and it is, for instance, used in the Unix tool grep. So how efficient is this algorithm? This algorithm runs in the worst case complexity of O of the size of R times the length of U. So what does this mean? This big O notation means that the complexity is basically a constant factor of the function given here. So basically the time complexity is the length of the regular expression times the length of the input word. If you think of the regular expression as fixed, so you have a particular regular expression that you're looking for, then you can think of this as a constant, and then you see it's just a linear function of the length of the input word. We're now going to use Thomson's word matching algorithm in order to check whether this word you contains a subword in the language of the regular expression here. Now we have already transformed the regular expression into an NFA. This first part here of the NFA is the sigma star part. So if you recall, if we go back, then you see here that we take the regular expression R, we extend it with sigma star, and then we transform it into an NFA. And the state Q0 with the transitions A, B is the sigma star part. Here in the starting state Q0, we can read arbitrary words over the alphabet sigma. And then we have a lambda transition, and from state Q1, the actual pattern R starts. So from state Q1, we are actually reading a word in the pattern of R. Now, how do we check whether the word you contains a subword in the language of R? We are taking this non-deterministic finite automaton and we are going to do an on-the-fly construction of a deterministic automaton when reading U. Now, what's the starting state of our deterministic automaton? It consists of the starting state of the non-deterministic automaton plus everything reachable by lambda transitions. So in this case, Q0 and Q1 together form the starting state of our deterministic automaton. And I'm writing the sets of states here without set brackets and without comma in order to save some space. So think of 0, 1 as the set containing the state Q0 and the state Q1. Now the first letter of U is an A. So the question is, where do we go from this state when reading an A? So we have to check what states are reachable from 0 and 1 via an A path. Okay, let's start with Q0. What states are reachable from Q0 via an A path? Clearly Q0 itself is reachable again, but we can also take an A step followed by lambda, so Q1 is reachable again. And from Q0 we can also immediately take a lambda transition and then an A. So also Q2 is reachable. From Q1 via an A path we can also reach Q2, but this was already reachable from Q0 via an A path. So what do we get? If we read an A, then we get to a state that contains Q0, Q1 and Q2. And again, I'm denoting this set without writing a set brackets, and I'm just writing the number of the states without writing Q0, Q1, Q2. I just write 0, 1, 2. Now the next letter is again an A. So the question is again, where do we go from Q0, Q1, Q2 with an A path? We already know from 0 and 1, so from states Q0 and Q1, we get to Q0, Q1, Q2. So the only question is, what do we get additional from Q2? Additional from Q2, we get Q3 via an A path. So if we read an A again, we get to Q0, Q1, Q2, Q3. Okay, we read one more A. We again get Q0, Q1, Q2, Q3. From Q3 we can reach Q3, so we get nothing additional. We stay in this state. Now we read a B. So what can we reach via a B path from Q0, Q1, Q2, Q3? We can reach from Q0, we can reach Q0. we can also reach by a b and followed by lambda, we can reach q1, so we get q0, q1. From q1 we cannot reach anything with a b. From q2 we can reach q4, so we get q0, q1, q4. And from q3 we can reach q5 via b pass. So we get 0, 1, 4, 5. Now the next letter of our input is A again. So what do we get from q0, q1, q4, q5 if we read an A? From q0 and q1 we already know we get q0, q1, q2. From q4 via an A we get q5. And from q5 via an A we don't get anything. There's no A transition from q5. So we get q0, q1, q2, and we get q5. Now we read again a B. So what is reachable from q0, q1, q2, q5 via B path? From q0 we get again q0, and with a b followed by lambda we also get q1, so we get q0, q1. From q2 we get q4. From q5 we get q6. So we get q0, q1, q4, q6. And this state is a final state in our DFA because it contains a final state of our NFA, q6. According to Thomson's algorithm, we stop as soon as we have reached a final state. So this shows that we have been successful. We have found an occurrence of our pattern described by the regular expression in the word u. So now we know that there is an occurrence of the pattern in the word u. But where is this occurrence? So we can use backtracing in order to extract where we have found the occurrence. So this is our input word u, just stretched out a bit more. So it's A, B, A, B, B, B. We did stop reading after this B here. So this was the last letter that we've read. And now what do we know? We know that we have started in a starting state q0 and we have ended after B in an accepting state. There's only one accepting state in this set, and that's q6 here. So we know that we have ended in q6. Now we are going to backtrace. We are going to look where did we come from reading a B. So if you're on q6 and we have read a B, we must have come from q5. And indeed q5 is among this set of states. If you're on q5 and we've read an A, then there's only one possibility. We must have come from q4. And indeed q4 is in this set of states. From q4, when reading a B, there's two options. We might have come from q4 or from q2. Now, where did we come from? We check. We were in this state of the DFA and we came from this state. Now, we have two options, q4 or q2. q4 is not in this set of states, but q2 is. That means we must have come from the state q2. Now from q2 we have read an A, so we must have come from q1. From q1 there's only a lambda transition, so we came from q0 without any input letter. And in q0 we came from q0 reading an A, and again from q0 reading an A. Now, how does this help us to see where our pattern has matched? The crucial point is that we see here that we stood in q0 for the first two letters A. That means this is this sigma star part that we are reading. And only after this lambda transition, the actual word in the regular expression R started. So now we can deduce that this part here corresponds to the word in the regular expression that we have found. So this begin part here, AA, this is the prefix before the regular expression has matched. And then the subword ABAB, this ABAB, this is the part that is a subword in the language of the regular expression. So that is where we have found the occurrence of the pattern. So the Thompson word matching algorithm is a very efficient algorithm for finding matches in text. However, a word of caution is needed here, because if you're using standard regular expression libraries, such as from Java, Perl, PHP or Python, then these libraries do not always use this efficient algorithm. These libraries often use algorithms that are exponential in the length of U. So that means that the running time of the algorithm in worst case increases exponentially with the length of the input string. And again, an exponential increase of the running time is something very bad. Luckily, these backtracking algorithms that are used there usually perform quite okay. So these exponential cases are rare. Nevertheless, the Thompson word matching algorithm is usually much faster, and it avoids this exponential blowup. So you might wonder, why do these standard libraries not use this clever algorithm? And partially the reason is that they try to go beyond the scope of regular expressions. So you have certain features in these regular expressions that actually go beyond regularity. So some of these libraries allow you to express that certain subwords that have matched should be the same. And comparing subwords to be the same is not possible with purely regular languages. Nevertheless, if you want to use just regular expressions for matching subwords, then you should be careful what libraries you're using. If you choose the right libraries that use the efficient algorithms, then you can be much faster. On this picture you see Ken Thompson and Dennis Ritchie meeting the back then US President Bill Clinton. So you see that doing computer science research really opens doors. You may even meet the US President if you want to. Ken Thompson and Dennis Ritchie have together won the Turing Award in 1983 for the operating system Unix. And Dennis Ritchie is also the inventor of the programming language C. The Turing Award is a very prestigious award in computer science. It's basically the Nobel Prize of computer science.